Alright, so we use vector addition for physical quantities that it would be equivalent to take the x direction path and the y direction path that would get you to the same place as the diagonal path that you see represented in the vector. And so what I'm going to start out doing here is I'm just going to kind of diagram these things out. So if I go this far in the horizontal direction and then I go this far in the vertical direction, that will take me to the same place as this diagonal vector that's given here. And I'm going to do the same thing. So it's always you start at the tail of the vector and go to a point that is vertically aligned with the head of the vector, and then you're going to draw the vertical vector to get you to the head of the vector. Now, something that I love about working on the computer here is that I can easily show you that it doesn't matter which way you draw these, as far as like you can move them here and it makes exactly it gets you exactly the same place. And that's part of the magic of the vector addition, is that adding those two vectors, no matter what order you add them in, gets you to the same place as this diagonal vector. Now, we need to do a little bit of trigonometry to figure out the value of each of those. We call them components. So for the horizontal components, let's see, this one, so the hypotenuse is given, and this one is adjacent to the angle, and we know the hypotenuse, so that would be a cosine function. And so what we would know, like for math or whatever, you would know that cosine of 40 equals adjacent over hypotenuse, so that would be like the unknown that we don't know over 3. Now, a little bit of simple algebra here is going to tell us that the unknown is going to equal 3 times cosine of 40. So most of the time when I write these out, I'm just going to kind of skip that little bit of algebra rearrangement there, and I'm just going to go, okay, hypotenuse times cosine of 40. Whenever you do calculations with this stuff, make sure that your calculator, Desmos, whatever you're using, is in degree mode if you're putting angles in degrees rather than radian mode, because things will not go well if you do it in the wrong mode. Okay, that one is going to be 3.5. That's adjacent. So it'll be 3.5 cosine of 17. And now let's switch back over to the blue. So this will be 3 sine in 40, and this one will be 3.5. Oops. All right, and that one will be 3.5 sine of 17. All right, and I have already done the math on these, so I can just tell you what they're equal to. All right, so 3 cosine of 40 is 2. I'm going to go 30, 2.30, and 3.5 cosine of 17 is 3.35. And then 3 sine of 40 is 1.93. And yeesh. Okay, and 3.5 sine of 17 is 1.02. Oh my. Go away. Sorry. Problem with the touch screen. Okay. 3.570. Yeah, 1.02. All right, now all of these quantities have units of meters per second, and I'm just not writing them just yet. Now, the kind of last thing that we need to do here, well, not totally last thing, there's the first last thing that we're going to do here is we're going to sum up our x and our y directions, our vertical and our horizontal directions. So I'm going to sum up the x direction, and then I'm going to sum up the y direction. So for the x direction, I have 2.30 pointing to the left. So that's negative. We generally, left is negative in math, right is positive unless told otherwise. Okay, so negative 2.30. Now, you're going to notice there's a subtraction sign on this particular problem. So what you're going to do here when you subtract a vector, that just means you make both components of the vector negative when you add them together. So this 3.35 that is positive as shown, when you subtract that, it's going to be negative. So we're just going to go minus 3.35. And we're going to do something similar for the y direction. So we're going to sum up. That's what that squiggly thing that looks, I think it's a Greek letter, epsilon maybe. Don't hold me to that. No, it's a sigma. What am I talking about? That's a sigma. Greek sigma there is telling you to add up all the things in that particular direction. All right, so similar deal here. 1.93 is directed downward, so it is negative. And then this 1.02, sorry, 0.93. Okay, this 1.02 is directed upward, but then we're subtracting it, so it's actually negative. So we're going to do negative, or minus 1.02. All right, so now we have components of our resultant or added together vector. However, I like to visualize this stuff. So the thing that helps me with this, I'm going to draw this thing. So 5.65 is x direction. So that is going to be, hopefully I'm still red here. Good, I am red. Okay, so 5.65 to the left. Okay, and then we're going to be, and I know I'm not to scale with all my other stuff up here, but, and then we're going to be 2.95 down. All right, and that's going to give us a resultant vector that looks something like that when you put the two together. So now what we need to figure out is we need to figure out the angle, the unknown angle here, and we also need to find the length of this vector. So right triangle trig, it's not even really, I guess it's trigonometry, it's sort of trigonometry. It doesn't have sine, cosine, and tangent in it necessarily. But just applying Pythagorean theorem is totally sufficient to figure out the length of the hypotenuse. So I'm going to do that now. All right, so Pythagorean theorem gives you 6.37 for the length of the hypotenuse and 6.37 meters per second. And then the angle, we would probably most conveniently use inverse tangent. But really, now that we know all the legs or all the sides of the triangle, you could pick your, whichever trig function you like the best. I prefer to use the values that, like this is a calculated value from those two values. So I would prefer to use the values that I have calculated less on in case I made a mistake on this one. But anyway, either way, you should end up with the correct answer. And generally speaking, when they score stuff on the AP Physics exam, if you do the right thing with the wrong number, usually they give you some grace for that. So anyways, last thing here, I'm going to show this in green. Hopefully, maybe, please let me click. Okay, let's try it again. There we go. Okay, now I've got the green. All right, so I'm going to show this one in green. So we're going to do tangent. Tangent of the unknown angle, I'm just going to call it theta. Let's call it. Yeah. Alright, so tangent of theta is going to be opposite over adjacent, which would be 2.95 over 5.65. Alright, and the way that you solve for theta here is you're going to do inverse tangent. So theta is going to equal inverse tangent. Sorry. Alright, there we go. Oh my goodness. Alright, so it'll be inverse tangent of 2.95 over 5.65. And I'll plug that into decimal. Alright, and pending I did correct math here, that angle is now going to be 27.6 degrees. Now, if you've drawn the diagram, you don't really have to go any further than that, but if you're just stating this outright, you would say that it is 27.6 degrees below the negative x-axis, because if you imagine a coordinate system here, the origin would be where the vector originates, and the negative x-axis would extend out here, and so this angle is 27.6 degrees below that negative x-axis. Now, this isn't fun without actually looking and seeing if I got the same answer as the answer key, and whenever I made this answer key, it does appear that I got the 6.37, and it looks like I got 62.4 is the angle, but if you look at the diagram that I drew, the way I reported the angle is a little bit different. So I reported 62.4 degrees from the negative y-axis, or 62.4 degrees to the left of the negative y-axis. So basically I'm reporting the, hold on, it's either supplement or complement. So here I'm reporting the complementary angle. That just means that it, would add up to 90 with the other angle that I got. So, if you add 62.4 to the answer that I reported over here, this guy, 27.6, you do get 90. So this is fine. It's just a different way of reporting the answer, and either of those would be acceptable. So I hope you found this video helpful, and have a good day.